Okay, Chem 30, here is your notes on section 14.1. We know how to balance our redox reactions and all of that. Okay, now we're going to actually look at application. Where do we use redox? Why does the transfer of electrons matter? Okay, so that's chapter 14. We're looking at electrochemical cells. Okay, and so we'll just start talking about cells and batteries. And so background, so electric cell is a device that continuously converts chemical energy into electrical energy. So two or more cells joined together is a battery. So in this case, we have a zinc copper battery because it's a bunch of cells put together. Okay, it can also be stacked. So again, as long as we have our cathode and anode, which we'll talk about, but and then something like some sort of in this case, like a electrolyte or paper soaked in some sort of electrolyte between the plates to kind of allow the charge to move. Okay, Volta's discoveries of current electricity led to many advances in physics and chemistry. Okay, the disposable battery is what we now call, or what we call in chemistry, a primary battery. So a primary battery can't be recharged. Rechargeable batteries would be then the secondary batteries. So basic cell design and properties. Each electric cell is composed of two electrodes. We have a solid electrical conductors, the electrodes are solid electrical conductors. Okay, so the metals that make up like the batteries, so like if we look back up here, okay, like the copper and zinc, and same thing, copper and zinc here, those would be our electrodes. Okay, and then one electrolyte, that's our aqueous solution. That's a conductor. So it's usually an acid or some sort of electrolyte, like or a salt. Okay, the cathode is the positive electrode and the anode is the negative electrode. So of our two metals, one will always be positive, one will be negative. Okay, again, the way to kind of remember cathode is positive is this T here. Okay, T meaning positive. Okay, and then anode is negative. If you know one, you should know the other. Okay, the electrons, when they're moving through a battery, they always go from the anode of the battery through external circuit to the cathode. Again, that's why like a battery only works when it's plugged in and the two cathode and anode are connected through some sort of external circuit. Okay, a voltmeter can measure the energy difference per unit charge. Okay, or also called the electric potential difference or the voltage. Okay, how many volts? It's measured in volts. Capital V is our unit. The voltage of a cell depends mainly on the chemical composition of the reactants of that cell. And so now when we look at in our data booklet where we have all of our reduction equations, they have a little number of voltage along the side. We're going to use those to kind of figure out what the cell's overall voltage is. Okay, and then electric current is measured in amperes, okay, by an ammeter, and is a measure of the rate of flow of charge past the point in the electric circuit. So how many electrons are going past that point in the circuit. Again, and the power of a cell is the rate at which it produces electrical energy, and it's measured in watts. Again, it's calculated as the product of current and voltage of the battery. So we're going to kind of go over how all of these are calculated later when we talk about kind of cell stoichiometry and so on. Okay, but in basic, okay, we always have our anode and our cathode of some sort of electrolyte, and then if it goes through whatever type of meter, so whether it's a voltmeter, which would then measure volts, okay, if it's an ammeter, it would measure current, okay, and yeah, so on. Okay, and so the electrons, again, they're negative charge, so they're pushed away from the negative side and go into the positive side. Okay, and then just some different quantities in SI units. So the unit for charge, okay, is coulomb. Okay, measured, or like the symbol for coulomb is capital Q, symbol is capital C. Okay, the current, the symbol is I, okay, measured with the ammeter, okay, and then the unit is ampere, okay, and So capital A is the unit symbol. 1 amp is equal to 1 coulomb per second. Okay, potential difference, capital V, it's measured using a voltmeter, its unit is volts, okay, and 1 volt, okay, is equal to 1 joule per coulomb. And then power, symbol is P, it's measured in watts, okay, and 1 watt is equal to 1 joule per second. Then energy density, we won't see much of this, but if it's there, okay, is just joules per kilogram, okay, is the unit. Okay, next page here. So we have, again, we talked about earlier, primary cells are just batteries that cannot be recharged. Okay, so dry cells, alkaline cells, mercury cells. Okay, most of the cells we kind of use now are secondary cells, like when you think about charging your phone or anything like that, we're using those types of batteries. Okay, they use electricity to reverse the chemical reaction. So a nickel cadmium cell, a lead acid cell, okay, so like in your car battery. Okay, these can be recharged, okay, if the products are stable with no further reaction occurring, and if the products are able to travel through the electrolyte towards the appropriate electrode. Basically, we're just reversing the reaction, okay, for secondary cells but we have to add energy in order to reverse that reaction. Okay, a fuel cell, okay, is a special type of cell. Basically, it's producing electricity by the reaction of a fuel that's continuously supplied to keep the cell operating. Okay, so the example here, okay, would be like a hydrogen oxygen gases are the fuel that go into this fuel cell, and as long as they continue going in and out, okay, it will it'll give off the charge and light up whatever you want to light up. Okay, so it's basically a battery that can refuel, and so instead of like charging it, it's just using fuel to give off this reaction and transfer those electrons. Okay, so yeah, instead of a container with chemical reactants sealed inside, the reactants flow into a fuel cell, okay, and the products flow out. Okay, examples are aluminum air cell. Okay, commercially viable fuel cells today are usually acid electrolyte cells, such as phosphoric acid fuel cells, which can produce enough electrical energy for the needs of a small city.